Good morning, beautiful people. I am Bins, and welcome back to the Shapez BEASTMAM series. Last time, we had a look at how we handle painting of flat shapes on the physical layer. Today, we're going to close that topic and start looking at the wiring. The topic of wiring for the flat piece factories is quite extensive and will therefore span a number of videos as well. So, we're going to dive back down to the section level, and in this first section of our new topic, I want to talk about preliminary rotation. Bins, what does that mean? For this video, I think it's important to keep in mind what we are actually doing. Keep in mind the bigger picture. And that picture is that we've set up a rather inflexible and one-sided factory on the physical layer. More precisely, we determined that we would create a smelter and cutter module where if we needed a normal cut, it would be a vertical cut, and if we needed to laser cut, we would always cut out the top right corner of the shape. So instead of trying to adapt our cutters to somehow cope with any orientation that the input shape may have, we decided to flip that dependency around. The shape has to conform to the cutters and not the other way around. And the way we're going to do that is by rotating the input shapes before they go in, and then rotate them back afterwards, right? Now, instead of building additional rotation modules on the physical layer's input lanes, I decided to actually let the wiring do the heavy lifting. We are going to analyze the input shape on the wiring layer, determine how its rotation fits the cutters, and then rotate the input signals if necessary rather than the input shapes. All right. Now, I'm gonna be honest with you. Today's video might challenge your analytical thinking skills a bit. It's definitely one of the more difficult things that we will review in this video series, so I'd say fasten your seatbelts and grab a cup of coffee. So we need to somehow rotate our input shape so that it's compatible with our cutters, right? And therefore, we will need an analysis module that processes the input. We need to find a way to tell the machine, hey, you need to rotate this thing 90 degrees clockwise or whatever before you start creating it. And the only thing we've got to work with is the actual input shape itself. We don't have any other info. So, how do we get there? Well, let's look at the paradigm again and try to figure this out together. Let's look at all of the possibilities individually, and let's determine how they need to be rotated in order to fit the cutters. All right. If we've got any one of the top two scenarios, then we don't need to rotate anything. If we've got the third scenario, then we don't need to rotate anything either. However, keep this in mind, technically, if we were to rotate this 180 degrees, then cut it, and then rotate back 180 afterwards, that would also work. Similarly, for the fourth scenario, both a 90 degrees clockwise and counterclockwise rotation would equally work. Keep this in mind as it will be important later. For the third group, which requires a laser cutter, we don't need to rotate if the cutout is in the top right. If it's in the top left, we rotate 90 degrees clockwise. If it's in the bottom left, we rotate 180 degrees. And if it's in the bottom right, we rotate 90 degrees counterclockwise. For the last group, we don't require a rotation if the two smelted pieces occupy the left half of the shape. And that means that if they occupy the bottom, we rotate 90 degrees clockwise. If they occupy the right half, 180 degrees. And if they span the top two pieces, then 90 degrees counterclockwise. All right? Now, here is where we will start thinking outside the box. For all of these shapes, we're going to consider its halves, and for each half, we're going to ask the question, are the two quadrants on this half smelted, yes or no? If they are, we will write down a 1. And if they aren't, we will write down a 0. And we will also make sure that we use the same sequence on all of them for consistency's sake. In order, each time, we will look at the right half, the bottom half, the left half, and finally the top half. In that order, okay? So in the first shape, are the rightmost two quadrants smelted? The answer is no. Therefore, we write down a 0. Next question, are the bottom two quadrants smelted? The answer again is no, so another 0. In fact, nothing in this shape is smelted, so our code is quadruple 0 for the first shape. The second shape, the blue one, is also easy. Everything is smelted, and therefore we get quadruple 1. For the third shape, first question, is the right half smelted? Well, in this case, the answer is yes, so we write down a 1. Is the bottom half smelted? No, therefore 0. The left half is smelted, and the top half isn't smelted, so another 1, 0 for our sequence. Let's do this for all of the shapes in our paradigm now. What we have obtained is essentially a unique 4-digit code for each scenario. And not only that, but we also know how each 4-digit code translates to a given rotation that we need to apply to the input. All right? Next, let's figure out a way to somehow obtain these codes on the wiring layer. And how can we do that? Well, the question we have asked is, are two given quadrants smelted or not? So in order to set this up on the wiring layer, we can set up a smelt detection module. So let's move to the right. A smelt detection module works as follows. We're going to take the shape, we're going to split it in half. We're going to take this output, we're going to rotate it 90 degrees, and then we're going to split it again. Right now, we are regarding the right half of the shape. And as a matter of fact, I'm going to make it easier on ourselves. I'm going to employ my sequence of circle, rectangle, square, windmill, right? So that we know what we're looking at. So in this case, we are looking at the right half of the shape. We're going to rotate that, we're going to split that, and then we are going to stack that together, like so. And then we are going to compare that to the input shape that we were given. No, not yet, because we've rotated this, so we need to rotate it back. As a matter of fact, this is a clockwise rotation, so we are going to do a counterclockwise rotation. Right? And now, this is the signal we get for an output. We are going to split this half, we're going to stack it back together, and then we are going to see whether or not the result matches the input. If it does, then it means that the quadrants were not smelted. So I'm going to put a NOT gate here, and the NOT gate makes sure that a 0 means not smelted. For the right half of the shape, the two quadrants on the right half of the shape are not smelted. All right? And we are simply going to repeat that for all of the shapes. So if we rotate this counterclockwise 90 degrees, then we can repeat this to check the bottom half of the shape. All right? Let's pretty this up a bit, like so. And now we do the exact same thing. Contrary to the right half of the shape, the bottom half is smelted. Those two quadrants are smelted. And if we take them apart and we stack them back together, then we are going to break the smelt that was there. And that is no longer going to match our input because we've broken the smelt between those two pieces. And that is how we can do smelt detection for a pair of adjacent quadrants. So thanks to our NOT gate, here the answer is yes, 1. Our bottom half of the shape is smelted. And now we can repeat this for all of the corners. Okay? Now let's see how that checks out with our actual codes. I can get rid of this, and I'm going to put a few displays here. And let's look at the shape we've taken. We've taken a shape with a horizontal cut right here. And the code we get is 0101. Now the question is, does that match what we have here? And the answer is yes, we have 0101 for a shape that has a horizontal cut. Let's do some more examples, right? We take this shape, and the code we should be getting is 1001. Let's see if that's the case. We put this in. Whoops. That is not what we want. Let's try that again. Thank you. And the code we get is 1001. Works like a charm, doesn't it? Let's try a final one. Why not this one? The code we want to see is 0001. Do we get that? The answer is yes, 0001. Exactly. So now we've got a wiring module that takes an input shape and it outputs 4 1s or 0s just the way we did it empirically before. We've now got a module that can create this list for us. And now we're going to try and find patterns. Let's pull up this worksheet right here because that will make it a bit easier to work with. And I am also going to flip the 1s and 0s like so. There we go. Why do I do that? Well, because if I turn the 0s into 1s and vice versa, then I can also get rid of the NOT gates that we put on our output lanes right here. Let's reconnect these lines like so. And that is going to correspond to this list again. Now let's get both on screen. There we go. And now we're going to try and see if we can spot any consistencies or patterns, or if there is anything else we can learn from it. The first observation we can make is that we actually don't need to take into account the first 2 cases, right? If the shape is fully smelted or not smelted at all, we won't require any of the cutters, and therefore it doesn't matter whether we rotate the input shape or not. So, as a matter of fact, these first 2 scenarios, we can disregard them completely. And the next 2 scenarios, they offer us a bit more flexibility than the remaining ones do, so we're going to skip over them for the time being. We're going to look at the rest. In the remaining cases, we are limited to 1 single rotation that we must abide by if we want to obtain the correct result. So let's look at the 2 90-degree cases first. What do they have in common? Let's make this a bit bigger. If we look at these 2 cases, what do they have in common? Well, I don't know if you spot the same thing I do, but these 2 codes both end in 011. Okay? And now the question is this a distinguishing criterion? In other words, is there any other code that also ends in 011? And the answer to that is no. Look at the list yourself. There is no other code that ends in 011. So this means that if we have a code that ends in 011, then we must rotate the shape 90 degrees before it goes in. And I'm going to make this yellow. Next, let's look at the 180-degree cases. If we look at those, is there anything we can see? Well, I see that the first 3 digits are 0, 1, 1. And again, if we compare that to any other scenario, there is no other scenario that starts with 0, 1, 1. So again, this is a distinctive criterion. I'm going to make that blue. No, I'm going to make that green. There we go. Now, let's look at the 2 cases where we have 270-degree rotations. If we look at this code and we look at this code, then, for example, I can see that both of them have 1, 1 here and a 0 for a last digit. 1, 1 and 0 for a last digit. And again, there is no other code that contradicts that. So, this is our defining criterion. Apparently this color is a bit too dark. Let's pick something lighter. And there we go. Excellent. And now let's look at the 0-degree rotations. I can see 1, 0, 1, 1, 0, 1. And again, there is no other code that has that. So that is also unique. Let's make that red. All right. Now, we still have to deal with our top 2 cases. So the question is there anything of this list that we can simplify? Can we loosen up these criteria in order to incorporate these 2 scenarios as well? And as a matter of fact, if I look at the 90-degree rotation and I look at the middle 2 digits, then I see 0, 1. And I see that here as well. A 90-degree rotation is a valid solution for this scenario. This scenario, if you don't remember, is the same as this one, right? If we rotate this 90 degrees, we cut it in half and we rotate it back, or we rotate it 270, cut it in half and rotate it back, that will both work, right? That's where that comes from. So, there is no other scenario, there are no other cases where our middle 2 digits are 0, 1 in that sequence. So as a matter of fact, these 2 ones, they are redundant. They don't matter. They are not necessarily a part of the distinctive criterion. And if we put that there, then we can incorporate this case. Now, let's see if we find something similar for this. We either need to rotate it 0 degrees or we need to rotate it 180. And one thing I could do, for example, is, look at the last 2 digits. The last 2 digits also work. If we look at this and this, there are no other sequences that end in 0, 1. There aren't any, so that also works. That is part of our, excuse me, not you. This is part of our distinctive criterion. And this is not. So we can get rid of that. These are the criteria that we can use. And now, all that we need to do is apply that here. If the last digits of our code are 0 and 1, then we don't need to rotate. So if you are not 1 and you are 1, then we can connect that to a 0-degree rotation. Are you with me? Next criterion, a 90-degree rotation. We need to get a 90-degree rotation if our middle digits are 0 and 1. So as a matter of fact, we can copy this. We can do just the same thing, and then we get a 90-degree rotation. There we go. Thank you very much. Next one, 180 degrees. If our first 3 digits are 0, 1, 1, then we get a 180-degree rotation. So what we could do, for example, is this, and then We could do that like this. And then excellent. And finally, for the last one, we need to have 1, 1, and a 0 right here. So let's see, we could put a 1, an AND gate right there. Pull this through, get an AND gate right here, get a NOT gate right here. And there we have it. So now let's see if that checks out, if we did everything correctly. We have this shape, for example. This shape is this one, right? And it needs to be rotated 270 degrees, 90 degrees counterclockwise, right? And that is the solution that we are getting right here. Isn't that cool? So, and basically, that is what I did. I made a simplified, more compact and more confusing looking version of this module, but other than that, it's the same thing. So if we now go back to our factory, we will see that if we follow this line along, right? Maybe let's take an example shape first. So how about, well, this one, why not, right? We have this shape going in, and first of all, we need to follow it along. This moves, this moves back a long way. It moves back all the way. Let's see, let's follow this along. And here is where the actual module is. The reason I put it here is because I have some space here, right? But here is where the transition or the process actually begins. This shape comes out. We are going to do a smelter analysis. We are going to get these 4 wires out, and then now here we have a conversion module. This is something we haven't talked about yet, but in our example, let's get back to it. There we go. In our example, I now decided to work with code shapes again. We talked about code shapes. If we have a 0 degree rotation, I decided to translate that in parentheses with a red circle. If we have a 90 degree rotation, that is going to be a yellow circle. If we have a 180 degree rotation, that's going to be a green circle, like so. And then finally a 270 degree rotation, that is going to be a blue circle. These are the codes I decided on. All right, so now let's get back to where we were. There we go. So in a slightly more compressed and more confusing looking setup, that is exactly the same principle I am going to apply. If the shape needs to be rotated 270 degrees, like is the case with the input shape we've chosen, we are going to output a blue circle. 180 degrees, green circle, 90 degrees, yellow circle, 0 degrees, red circle. All right, so we have this lane, it goes out here, and this is now connected to this. We have a copy of our input line that goes here, and then in accordance with the output shape we've gotten from the module, we are going to choose one of 4 rotations. In this case, I am going to rotate it clockwise once. Then I'm going to paint it gray because we don't care about the colors for now. We're going to do the colors in a different bit of the wiring. And then we are going to send this rotated shape back. Currently, it's been rotated only 90 degrees clockwise, which initially is a bit confusing. However, this signal makes it all the way back to the hub, where in the end it will be rotated clockwise again and once again, right? We are going to look at these other modules later, but in the end we get an input shape and then we get a rotated form back from our module, and that is going to serve as the actual input. that operates the machines. So what do we see? Let's make this shape easier on ourselves. And again, we are going to use the system where the top right corner is a circle, the bottom right is a rectangle, the bottom left is a star, and the top left is a windmill. Okay, so our shape will look like this. Now let's go back again, and we're gonna have a look at the inputs. The shape that comes in is this one. The rotated form we get back is this, and then finally this. The square is going to be in the top right, which means we've had a 90-degree counterclockwise rotation. And now let's see how that comes out of the modules. There, I think we can pause it there. So what do we see? We get the circle in the top left, we get the square in the top right, we get the star in the bottom right, and we get the windmill in the bottom left. And that is a 90-degree counterclockwise or 270-degree clockwise rotation. So that is the way the shapes are going to be generated. They are going to be generated in their rotated forms. Right? That's what I meant when I said I don't have any extra rotation modules. We are going to send in the wrong shape because it will be rotated afterwards. And first we need to send in a shape that fits our cutter modules. So once the cutters have done their thing, the shapes will be rotated back to the orientation they need to be in. And in the end, after painting and stacking, these shapes are going to be the ones that we want. And there we go, right? This is the shape we're getting. This is the shape that we wanted. With the green square in the bottom right and the two smelted halves at the top, that is exactly what we are getting. So that's what I wanted to have a look at today. I thought that this was a pretty tough thing to do. I don't know if you agree with this, but it seems like one of the more complicated mechanics in this machine, because the things we have done with this input rotation, it's actually borderline, it borders on computer programming already. Right, so I think we've reached the end of our video for today. I think we can wrap it up. This is what I wanted to talk about, and I really like this topic because I think it's an excellent illustration of how far you can push this game if you set your mind to it. So I hope you had a lot of fun. If you don't want to miss out on upcoming videos in this series, then be sure to leave a like, a comment, subscribe, all that good stuff. And then I would love to welcome you again. For today, I am signing out. I've been Bins. Take care. Bye-bye.